Greetings, everyone. This is Jeff Wilkerson, professor of physics at Luther College, bringing you the next in our series of what to look for in the night sky the week of June 9th. This time around, what a terrible moon week we have. The moon starts just short of full on the night of the 9th, meaning it's up all night, washing the sky out from just after dark till morning. And it sits right next to Antares. So you want to go out that night to observe something, look at the full moon sitting just to the west, the bright orange star Antares in Scorpius. By June 15th, the evening at the end of the week, it's still 85% full. It will have waxed up to completely full. I think it's about 98% right there. It will have waxed up to completely full and waned away, but only down to about 85%. But that means it rises a little bit after dark, so you have a chance to observe some things in the evening sky before being completely washed out. But it also means what we want to focus on this week, as we always do when we have these moon weeks where there's a lot of moonlight washing out the fainter things in the sky. We focus on the brighter objects like the planets and the stars. So let's look at the morning sky. We looked at this a couple weeks ago, but they're even closer now. Saturn and Neptune. Saturn sits just below Neptune, and this pair sits somewhere south of the Great Square of Pagasus here. So we see the Great Square of Pagasus rising into the morning sky. We think of this as a fall object because it hangs high in the evening sky in fall. But here we are now, as we work our way into summer. We see the Great Square of Pagasus rising into the sky. We see Saturn as the yellow gold dot that's bright shining down below here. Pair of binoculars will show Neptune. It starts the week about 1¼ degrees that's separating the two planets, and by the end of the week you will have watched this move. If you track it every morning here this week, you'll see it down to just barely over 1 degree separating the two of these planets. If you have a very wide field eyepiece, a good wide eyepiece, 40 millimeter eyepiece, depending on the focal length of your telescope, you might be able to get both of these in the same field of view of your telescope eyepiece. Probably you can. So this is going to be fun to look at and to track these across here as that separation shrinks. This whole area rises about 2:30 in the morning. So you got a good window from 3 to 4 o'clock in the morning before it starts to get daylight. That's my time here. For us to be able to check this out. In the evening sky, we talked about last week, Mars was closing on Regulus, and it really closes on it this week. Regulus is the brightest star in the base of the sickle of Leo, and Mars starts the week about 4 1/3 degrees away, and it's right just barely over 1 degree separates the two by the end of the week. So you'll really watch Mars closing on Regulus. This whole area sets about somewhere around midnight. So sort of 9:30, as soon as it's getting dark, sort of 9:30 to 11 is probably your best observing window to look to the southwest. And you'll see bright red Mars there next to the bright star Regulus in the base of the backwards question mark. That is the head of Leo. That's Regulus right there. So Mars is closing in that direction. Now, back to thinking about the Saturn and Neptune sitting below the Great Square of Pagasus. So the Great Square of Pagasus is one of the iconic markers of the sky. We got this big box of stars. They're all pretty bright. They're all good second magnitude type stars. And there's not a lot interior to those stars, so it looks like a big empty square unless you have really dark skies. The upper left corner of this Great Square of Pagasus is actually the alpha star in Andromeda. Andromeda is the V that hangs off that direction. Alpheratz is that star. Algenib is this star. Markab is the alpha star. That's the gamma star in Pegasus. The alpha star is Markab in Pegasus, and the beta star is Shiak, is the upper right-hand corner star in the Great Square of Pagasus. Now, we can think about these stars because we have a chance to think about stars this week because we can't go out and see galaxies and nebulae and stuff so much. There's so much moonlight around. We think about stars. We've talked about this before. This is an HR diagram. If we plot how much light the star is emitting, how much energy the star is emitting out into space up this direction, and the temperature of the star increasing across this direction, we get a main sequence of stars that looks something like this. All of the stars that are in this main band, this sequence of stars that we call the main sequence, they're getting their energy primarily from fusing hydrogen into helium way down in the core. And the bigger the star is, the hotter the star is, and the more luminous the star is. More mass pushing down means you need more higher temperature for gas and radiation pressure holding that star back up, and that causes you need a higher temperature for that higher radiation pressure just to get the mass pushing down. causes you to have a higher temperature, and that causes more nuclear reactions, hydrogen into helium in the core up here. So we see these very luminous, very bright stars up here. 3 of these stars, Algenib, Markab, and Alpheratz, are all right here in the upper main sequence. Big, bright. Those stars are relatively rare. So we see these big, bright stars on the sky, and we see a lot of them here in the upper main sequence, and we think, wow, those are pretty common stars. But they're not pretty common stars. We just happen to be able to see them a long ways through space because they're so bright. The stars down here are much less luminous, lower temperature, not radiating nearly as much energy into space, not nearly as bright, and there's lots and lots and lots of them. For every one star that's up here, you've got hundreds or thousands or more stars down in here. Lots of these stars, you just can't see them because they're so faint. You only see the ones that are relatively close to us. They get too far away from us. It's like having, I don't know, I didn't do this calculation in advance, but it's like having a 1,000-watt light bulb and a 1-watt light bulb, or even more, greater separation than that, a bigger brightness. Somebody starts walking away from you, the 1-watt light bulb disappears pretty quickly. The 1,000-watt or the 10,000-watt light bulb you can see for a long, long, long ways away from you. And so you can see these stars, and they look common. So you have 3 of these main sequence stars. Now, when a star fuses all of its hydrogen into helium in its core, then what's going to happen is you're not generating energy down in here. You're going to start to cool down a little bit. When you cool down a little bit, that pressure that's holding the star up starts to drop. The star starts to collapse. But when the star starts to collapse, it converts gravitational potential energy into thermal energy, and it gets hotter in the core, and you get hot enough for hydrogen into helium to start fusion, to start occurring in a shell, a thin shell around that inert helium core. That we call a red giant star. That's a star that has moved over here on this diagram and is now a giant star that's getting its energy primarily from this shell fusion, and Schiat is over here. So Schiat has left the main sequence and is over here becoming a giant star, with shell hydrogen fusion being its primary form of energy production. So when you see these 4 stars, you can think about what's actually physically going on with these stars. It's just kind of a fun way to think about it. Let's find some new stars here too. We hop about 5 degrees up off the upper right-hand corner away from Schiat, and we get to Matar, the Eta star in Pegasus. It's a 2.9 magnitude star. Go 1.5 times as far again, about 7 3/4 degrees, and we come to Pi. Pi is a 4.3 magnitude star. Now, if we drop 9 degrees down, so you've gone up here, then make sort of a right angle and drop 9 degrees down. Remember, 9 degrees is about a fist width at arm's length. You're going to come to 4.1 magnitude Kappa Pegasus, Kappa Pegasi, and just above there, about 3 degrees or 4 degrees is 4.5 magnitude. So you have 2 stars that are about 4th magnitude stars. You got good dark skies, you can see them. 4.1 and 4.5. That's the Mu star in Cygni, in Cygnus. So Mu Cygni is way out on the outer reaches of the constellation of Cygnus. Right there. So we got 4.1 and 4.5 magnitude stars. Mu Cygni is a binary star with relatively high eccentricity, and so is Kappa Pegasi. So Kappa has about an 11.6 year period, but with this high eccentricity of 0.6. So it's an elongated orbit, which means you can get a separation of these stars up to as much as 5 arc seconds or 6 arc seconds, but it's only about an arc second right now, and you're going to have a really hard time splitting that into individual stars. Go ahead and try, why not? But you're going to have a hard time seeing that as 2 stars because the 2 stars are so close together right now in the sky. Now, the brighter of those stars, which you usually call the A component, but in this case is the B component, but we won't go into that too much. The brighter of those 2 stars in that binary system is also a spectroscopic binary with something on the order of a 5-day period. I should have looked that up. Something on the order of 5 days. We've talked about spectroscopic binaries before, where you see 2 sets of spectral lines, dark lines, on top of a bright background in the star. One star's coming toward you, one star's moving away from you. You see a blue shift, so the line shifted to shorter wavelength. Red shift, line shifted to longer wavelength. These are all over the sky. We talk about them almost every week because we run across them. And so the brighter component of Kappa Pegasi is a spectroscopic binary with 5 or 6 day period. Mu Cygni is also a very elongated, high eccentricity binary star, and it's now opening up But it's got a longer period. It's got a very long period, but it's opening up out right now. And so it's about 2 arc seconds. You got a chance. You got decent skies. Go out and try to use your telescope to separate this 4.5 magnitude mu Cygni into its component stars. It should be about 2 arc seconds apart. Got to have good stable seeing, so the atmosphere not too turbulent above you when you're trying to pull this apart. Fifth and sixth, they're about equal magnitude star, a little bit brighter than a fifth magnitude star and down to about a sixth magnitude star. I say about equal, but that's 2.5 times. One of them's 2.5 times brighter than the other. So you'll notice that brightness difference if you can pull them apart. So that's what we got for you this week. A lot of moon, a couple of interesting planets, some interesting planet stuff going on in the sky. Let's start to enjoy the Great Square of Pagasus and think about stellar evolution and think about what's powering the stars here and go see if we can find a couple of binary stars. Very tricky. That one's impossible, I think. Maybe we can do this one. So tricky binary stars, but let's learn some new stars across here. Mu Cygni, Kappa Pegasi, Pi Pegasi, and Eta Pegasi would be the stars we can look for up off the western edge of the Great Square of Pagasus. So this is what we got for you. As always, everyone, thanks for watching, and we hope you have a great week ahead.